Hello everyone, welcome back to learn the axially loaded member. In the previous lesson, we have studied the global buckling critical load of an ideal axial compression member and discussed the influence of various imperfections on its stability bear capacity. In this lesson, we will study the calculation methods of the overall stability of the real axial compression member. Firstly, let's look at the figure 8. Figure 8 shows the comparison results of the compression force midspan deflection curves between an ideal compression member and a real compression member. In the figure, curve 1 is the load deflection curve of an ideal axially loaded compression member found in the mode of elastic flexural buckling. It can be seen that the critical elastic flexural buckling force of the column is equal to order critical load NE. Curve 2 is a load deflection curve of an ideal axial compression member that fell in the mode of elastoplastic flexural buckling. In this curve, the critical elastoplastic flexural buckling load of the column can be determined according to the tangent modulus serial, with the critical load being as Nt. Further, curve 3 is the load deflection curve of the real axially loaded compression member. For such a case, it is necessary to determine the ultimate limit state of the member at the failure time first, then determine its critical buckling load. Here, we will introduce two criteria to determine the ultimate limit state of the real column and establish corresponding calculation formula for the global buckling critical load. These two criteria are edge fiber yield criteria and maximum strength criteria, respectively. Firstly, let's see the concept and the principle of edge fiber yield criteria. According to the edge fiber yield criteria, the flexural buckling critical load of the real axially loaded column can be determined according to the state when the stress on the compressive edge fiber at the midspan of the column reaches yield stress. In curve 3, point A corresponds to the edge fiber yield instant. Thus, the force NA at point A can be adopted as the maximum stability bear capacity of the real column. The edge fiber yield criteria is generally suitable to determine the global buckling critical load of the cold form steel or build-up column. Next, let's go on to learn the concept and the principle of the maximum strength criteria. In the maximum strength criteria, the ultimate limit state of the axially loaded column is defined as the instant when the column reaches its maximum bear capacity. In such a state, all the stress on the cross-section at the midspan of the column reaches the material's yield strength. In the curve 3 mentioned above, the ultimate limit state of the real axially loaded column generally corresponds to point B. Thus, the compression force NB at point B can be taken as the maximum overall stable bear capacity of the column. Then, the critical stress of the column can be obtained by dividing this critical force by the column cross-sectional area. The maximum strength criteria is usually suitable to determine the stability bear capacity of the solid web axial compression members. After learning the method to determine the global buckling critical load of the column, let us further look at the design methods for the overall stability of the axially loaded column. In the design of a steel structure, we usually use curves which are called column curves to determine the maximum stability capacity of axially loaded compression member. These column curves are defined as the function curves between the critical stress sigma CR and the column slenderness ratio lambda. Since the value of the critical stress sigma CR is affected by imperfections such as initial crookedness, the eccentricity of load, and the residual stress, The column curves are further divided into multiple groups to consider the influence of these imperfections. In the steel structure design standard in China, the column curves for actually loaded compression members are determined according to the maximum strength criteria. Considering the influence of both initial coordinates and the residual stress, and based on a large number of theoretical calculations and engineering experience, 4 column curves, namely curve A, B, C, D, are obtained according to the cross-section form adopted for a column. In these 4 column curves, A, B, C, D correspond to 4 different types of cross-sections. Curve A is used for columns having a cross-section with the smallest residual stress and the initial coordinates. Curve C is used for columns having a cross-section with large residual stress and the initial coordinates. Curve B is used for columns having a cross-section between type A and C. Curve D is used for columns made up of thick plates, namely the plate thickness is greater than 40 millimeters. The specific cross-section classification of axial compression members can be referred to the corresponding design code. After we obtain the relationship between the section classification and the column curves, we can calculate the critical stress of actually loaded column according to the section category and the member's slenderness ratio, and then obtain its stability bear capacity. Next, let's discuss the global buckling calculation method of the actually loaded compression members. In the design, the compressive stress on the section of axial compression member shouldn't be greater than its global buckling critical stress. After considering the partial coefficient of resistance, the overall stability capacity of the actually loaded compression member shall be calculated according to equation 4-7. In equation 4-7, N is the design value of the actual compression force, and A is the gross sectional area of actual compression member. F is the design value of the compressive strength of steel. Phi is defined as the ratio of critical stress sigma CR to steel yield strength Fy, which is called the overall stability coefficient of axial compression members. This coefficient can be determined from column curves according to the value of the column slenderness ratio lambda. In order to be convenient for the calculation, the 4 types of column curves mentioned above were further converted into 4 tables in the design code of steel structure. In other words, the designer can directly check the data in these tables to obtain the value of overall stability coefficient phi for corresponding designed axial compression member according to the column section category and calculated slenderness ratio lambda. This greatly reduces the complexity of calculating the overall stability coefficient. In summary, in this lesson, we have learned the section classification, column curve, and the overall stability calculation of the actually loaded compression member. In the next lesson, we will learn the calculation methods of local stability of actually loaded compression members. See you next time.